In today's lecture, we're going to go over temperature. Thermal interactions occur when you have two blocks, one of which is warmer, than the other, and they're brought into contact. And then we're going to isolate them. And once they're isolated from their surroundings, we're gonna look at property changes that occur. So when all of these property changes stop, we're going to say that we are in thermal equilibrium. And temperature is a physical property that determines if our two blocks are in thermal equilibrium. So we have something which we dub the zeroth law of thermodynamics. And what the zeroth law of thermodynamics says is that when two objects are in thermal equilibrium, with a third object, they are all in thermal equilibrium with one another. The zeroth law of thermodynamics basically allows us to use thermometers to measure temperatures by saying, hey, these two objects are in thermal equilibrium with each other, with a third object, which means they're all in thermal equilibrium with each other, so this is the temperature. Any object can really be used as a thermometer, but to be used as a thermometer, you have to exhibit a change in a physical property with temperature. That property is called a thermometric property, and the substance is called a thermometric substance. We have something called the Kelvin and Rankine, so we now know what temperature is. What we're going to do next is define temperature scales. We have the Kelvin and the Rankine temperature scales. The Kelvin scale is an absolute thermodynamics temperature scale. It's valid over all temperature ranges. The unit is Kelvin, not degrees Kelvin, just Kelvin. And it's the base unit in the SI system so much like we have the Kelvin scale in SI units, we have the Rankine scale in English units, because so it's also an absolute thermodynamic cis scale. The absolute zero of the Rankine scale corresponds to the absolute zero of the Kelvin scale. Again, it is the base unit of temperature in the English units, and its unit is degrees R, which is degree Rankine. So to convert from the Rankine scale to the Kelvin scale, so your temperature in degrees Rankine is equal to 1.8 times your temperature in Kelvin. So much like we have to use absolute pressure in all of our thermodynamic relationships, we also have to use absolute temperature. So even though problems are typically going to list temperature in Celsius or Fahrenheit, you're going to have to use temperatures in Rankine or Kelvin to determine all of your thermodynamic relationships. So we also have the Celsius and Fahrenheit scales. The Celsius temperature scale uses units of degrees Celsius and is related to the temperature in Kelvin. So my temperature in degrees Celsius is my temperature in Kelvin minus 273.15, or just 273. The difference in temperature in both the Kelvin and Celsius scale are the same. So if you're doing a problem that involves the change in temperature, then you don't have to convert, but otherwise temperatures are in Kelvin. Much like Celsius and Kelvin, we have Fahrenheit and Rankine. The temperatures in degrees Fahrenheit is equal to the temperatures in degrees Rankine minus 459.67, or just 460. If I wanted to relate my temperature in degrees Fahrenheit to my temperature in degrees Celsius, it's 1.8 times my temperatures in degrees Celsius plus 32. So now I'm going to go over one quick problem where we use some of these relationships to get used to our temperature scales. We have air rising from a morning low of 42 degrees Fahrenheit to an afternoon high of 70 degrees Fahrenheit. We want to express these temperatures in degrees Rankine, Kelvin, and degrees Celsius. And then we want to determine the temperature change in degrees Fahrenheit, degrees Rankine, Kelvin, and degrees Celsius. So from degrees Fahrenheit to degrees Rankine, we have our temperature in Rankine is going to be our temperature in Fahrenheit plus 459.67. So our low is going to be 42 degrees Fahrenheit plus 459.67, which is 501.67 degrees Rankine. And our high is 70 degrees Fahrenheit was 459.67. It's equal to 529.67 degrees Rankine. So now I can go from degrees Rankine to Kelvin, where my temperature in Kelvin is equal to my temperature in degrees Rankine divided by 1.8. So my low is going to be 501.67 divided by 1.8, which is 278.71. And my high is going to be 529.67 degrees Rankine divided by 1.8, which is 294.26 Kelvin. And finally, we're going to go from Kelvin to degrees Celsius, which in degrees Celsius, it's my temperature in Kelvin minus 273.15. So my low is 278.71 minus 273.15, which is 5.56 degrees Celsius. And my high is 294.26 minus 273.15, so I get 21.11 degrees Celsius. So it asks for the temperature difference. I want to do it in degrees Fahrenheit first. Is 70 degrees Fahrenheit minus 42 degrees Fahrenheit, just 28 degrees Fahrenheit. I want to do it in degrees Rankine, which is 529.67 minus 501.67, which is 28 degrees Rankine. I want to, in degrees Celsius, we're going to have 21.11 minus 5.56, which is 15.55 degrees Celsius. And lastly, we're going to do it in Kelvin, which is 294.26 minus 278.71, which is 15.55 Kelvin. So again, as expected, our delta T in degrees Rankine and degrees Fahrenheit are the same, and delta T in Kelvin equals delta T in Celsius. That's it for this lecture. That's it for chapter 1. In our next lecture, we'll move on to chapter 2, where we start learning about energy, heat, and work.